In this video, we will practice determining and computing the rate law. So for every reaction, depending on how fast it goes or how slow it goes, we sort of quantitate that with a rate law. So the rate law, rate is just how fast the reaction proceeds, is dependent on the concentration. So more concentration, we would expect faster rate because there's more material that can go to products. It also depends on the rate law constant, which is lowercase k. And it also depends on how fast these decay. You see, A is going to decay to give you some of the products. B is going to decay, that will give you some of the products. So how do these decay? The way they decay is by the way they decay is through exponents. Okay, so the exponent can be either a zero order decay, the exponent is 0, a first order decay, the exponent is 1, or a second order decay, the exponent is 2. So it's the reactants, how much they have, the concentration, the rate constant, lowercase k, and then the order of decay of these reactants to give you products. So in this question, we're trying to figure out the rate law, which is going to be universal, any concentration. So the first thing here is our generic problem, a generic reaction. So the generic reaction will have the generic form rate is equal to K, the concentration of A raised to some exponent, you can call it X, and then times the concentration of the other reactant raised to some exponent Y. So these exponents X and Y are called the orders of the reaction, okay? Whether it's 0, first, or second order decay. So we also need to find out rate constant K and put it in the right units. Okay, putting it in the right units matters. So to get this type of problem and solving correctly, we're going to have to compare experiments. So here we have 3 trials. I'm going to compare experiment 1 and 2, or trial 1 and 2. So we'll try trial 1 over trial 2. And so that is going to be the rate 1. Here you have to be very, very explicit with your units because this lowercase k changes. So rate 1 over rate 2, comparing experiment 1 over experiment 2. And so the rate is equal to k times the concentration of A raised to the order X times the concentration of B raised to the order Y. That's for rate 1, experiment 1. Do the same thing for rate 2, experiment 2. Okay, now it's just a matter of plugging in the appropriate values for rate 1, experiment 1, rate 2, experiment 2. So I'll go ahead and do that. Rate 1 is 3.20 times 10 to the minus 1. So I'm going to put our units here. So the units are the trickiest thing with these rate laws. Units are molar per second, big M, moles per liter. And rate 2 is, and let's do this for rate 2, experiment 2. Put in my numbers here. Lowercase k rate constants cancel, and this to the power of x and this to the power of x cancels. So we're left with 1.5 divided by 2.5. That whole thing gets raised to the power of y. So 1.5 is the same thing as 3 halves. 2.5 is the same thing as 5 halves. So 3 halves over 5 halves is going to be, that whole thing is to the power of y. So we can easily solve for y, realizing that anything to the power of 0 equals 1. Right? Do you remember that rule from math? Anything to the power of 0 is 1. So the order of the decay for B is 0 order kinetics. Okay, so this is going to decay to give you products. That is 0 order decay, and the associated equations associated with that decay. Do not have to memorize those equations. All right, now let's figure out order x. So for that, let's go back to our data table. So to solve these problems, you need a data table like they've shown here. Let's compare experiment 1 and experiment 3. Okay, so experiment 1 versus experiment 3 to try to figure out order x, which is associated with the rate of decay of concentration A. Okay, remember our overall reaction is A plus B goes to products. Now we will compare trial 1 with trial 3. Rate is equal to K times the concentration of A. The concentration of A for rate 1, experiment 1 is 1.50 to the power of X. The concentration of B, the concentration of B in rate 1, experiment 1 is 1.50 to the power of Y. Okay, these are all in molars, moles over liter. Okay, rate 3, let's look at our table here. Rate 3, the concentration of A is 3 molar. So that's going to be 3 molar to the power of X. And then the concentration of B is 1.50 to the power of Y. We already know Y is 0, so it's kind of a moot point. And also rate 1, we can plug that in here, is 0.320 m over s molar over second. Rate 3 is double that, 0.640 molar over seconds. Okay, rate, kind of like miles per hour, but this time it's molar over seconds. So let's just rewrite this down here to make this more complete. Alright, so I plugged in comparing experiment 1 to experiment 3. The lowercase k cancels this, cancels with that. We already know y is equal to 0. We solved that previously. So now we have 1/2 to the power of x. That whole thing raised to the power of x. Remember, 1.5 divided by 3 is 1/2. So that whole thing gets raised to the x power. And this is also 1/2. So here, 1/2 to the power of x equals 1/2. This implies the order for x, which is associated with the rate of decay for A, is going to be 1. Now, let's go back to our rate law here. Going back to our rate law, we can plug in the x and y order. So A will decay with first order kinetics to give you products. Y will decay with B will decay with 0 order kinetics to give you products. Let's fill all this out here now. So we're not done yet. Okay, this is a common mistake. People think they're done, but they're not done because we need to calculate the rate constant lowercase k. So here's our rate law. Anything to the power of 0 is actually 1. So rate is equal to k times the concentration of A. Alright, because remember the order of decay, that exponent is 0. Alright, now let's figure out rate constant k. For that, we'll pick any experiment. Okay, we can pick 1, 2, or 3. They should be all roughly the same. Let's just pick experiment 2. Okay, though again I can pick 1 or 3. So let's plug in experiment 2, rate 2 conditions. So rate 2 for experiment 2 is 0.320 molar over seconds equals k. We're going to have to solve for k here now. And concentration of A is 1.50 raised to the 1 power. Raised to the power of 1. Okay, now you have to be very meticulous here with regards to your units. So k is going to equal to 0.320 m over seconds divided by 1.50 big M, which is moles per liter. So the big M cancels. So 0.320 divided by 1.5 will be the answer for lowercase k, the rate constant. So on my calculator, I'm getting an answer of about 0.213. Units here are seconds to the power of minus 1. So 0.213, the M over M moles per liter cancel. And we're getting 0.213 seconds to the power of minus 1, or you can say it's the same thing, 0.213 over seconds. All right, our final answer is this. We want to complete everything. Our final answer for the rate law for this problem is going to be rate equals, what did we get for k? We got 0.213 inverse seconds times the concentration of A. Times the concentration of B raised to the power of 0 is 1, so that just becomes 1. So this is our final rate law. You can actually test this out. So let's use some conditions here. Experiment 1. So if you take 1.50 times 0.213, you should be able to get and recapitulate the rate for experiment 1, which is 0.320. In fact, you can recapitulate, plug in these values to get the rates utilizing the rate law. That's what it means. The rate law is universal based on at a specific temperature. This is very much temperature dependent.